about constant solution or so-called equilibrium solutions. So when you have an ODE, the easiest type of solution you can think about is a constant. If the equation, the ODE, admits a constant solution, it may not have a constant solution. So, but if y of t equals some constant is a solution, well, that means it should satisfy the ODE, which means that if I plug in a instead of y of t, so once again, it's important to understand what I mean by a constant is a constant function. So y with respect to t as a function of t is just a constant, which it means it will look like a horizontal line if you were to plot it. If this will be a solution of the ODE, then I can replace y with that constant. And as we know, the derivative of any constant is going to be 0, right? So that means if you have a constant solution, it should be a solution of this equation. So if I set the right-hand side of the ODE with 0, and I can find y as a function, as a constant, that means that's a constant solution. So basically, to find constant solutions, you set f of ty equals 0, and solve for y. Now, that doesn't mean anything you get for y is a constant, right? It has to be a constant in the sense that it shouldn't depend on t, right? So let me give you an example. So suppose that your ODE is, let's say, t minus y times y minus 5, right? So if I set this equal to 0, if I set the right-hand side equal to 0, I get y equals t, not a constant, because it depends on t. And on the other hand, the other possibility is for this parenthesis to be 0, and of course we can get y equals 5, which is constant. Another name for constant solutions is an equilibrium solution, and I'll explain immediately why that's the case. But from this point on, the term equilibrium or constant solution is interchangeable, right? I mean, they mean the same thing. So equilibrium solution is because, think about this, if you actually imagine you reached a constant solution, let's suppose that you start at a point and then the solution approaches a constant solution. When that happens, the derivative becomes 0, which means that there is no more motion, right? That means the function neither increases nor decreases, which means whenever the derivative is 0, the motion stops, the dynamic stops. So it's important to know not only if there are constant solutions in an equation, but whether they are stable or not, in the sense that whether the other nearby solutions approach the equilibrium point or not, because that has predictive value, right? I mean, you can predict that the solution will stabilize at a certain value. And stabilizing means at some point the derivative is 0. That means that the solution doesn't change anymore. So we know how to find the constant solutions. Let's give another example. Suppose y prime is equal to y squared plus 1, y minus 3. Again, if you set it equal to 0, you notice that y is equal to 3 is the only constant solution. And finally, here's another example when you may have no constant solution at all. So if you have y prime equals, let's say, y squared plus 1, like before, times y squared plus 3. If you set it is equal to 0, we have no solution for y. That means there is no equilibrium. So, as I mentioned just now, one important thing to ask is whether these constant solutions or equilibrium points are stable or not. So let's actually write down a definition here, which we'll get back to it even when we study systems later. a constant solution or an equilibrium is stable if nearby solutions converge to it. That is, they approach the equilibrium point. In the single ODE case, in the single autonomous ODE case, this is just a matter of analyzing the sign of the derivative. So I'll show you with an example right away. But let's mention here the stability, or this can be established, the stability by analyzing the sign for y prime in the case of autonomous equation. That is, those ODEs in which the right hand side doesn't depend on t. Like that. So if your ODE depends on y only, if there is no t on the right hand side, you can easily establish this stability by simply analyzing the sign of f of y, that is to say, of the derivative. So before I show you the example, which is very easy by the way, let's actually anticipate why that's the case. Once again, if I have a constant solution, the derivative will be 0. Okay, if I start nearby that equilibrium point, I either move away from it or toward it, depending on whether y increases or decreases. Now we know from calculus 1 that if y prime, that is to say f of y, is greater than 0, then y increases. And if the derivative, or that is to say f of y, is less than 0, that means y decreases. So if I only care about the stability, I can simply look at the signs of f of y, and I can indicate with arrows whether the solution goes up and down. So this is the so-called phase line, which gives you a quick way to establish the stability of equilibrium points. So let's consider an example. Let's say y prime is equal to y minus 1, y minus 5, let's say. So notice that the equilibrium, the constant solution, if I set it equal to 0, are y equals 1 and y equals 5. The next thing is to actually draw a vertical line. I typically like to draw this vertically, although it doesn't matter, because the y values are typically represented on the vertical line, right, on the y-axis, right? So sketch first or label first the equilibrium values. Let's say 1 in this case and 5 over here. And then pick a couple of test points in between the equilibrium points to decide how the solution moves. So for example, if I pick a point above 5, let's say I pick 6, and I plug it into the y prime, right? So let's write here like a table of values, y and f of y, right? So let's say I pick 6. Then that gives me 6 minus 1, 6 minus 5, which is a positive quantity, right? So if I start with a point above 5, I know that the solution increases because the derivative is positive. So I can indicate this with an arrow pointing up. Then in between 1 and 5, let's say I pick a test point, whatever you like, any number between 1 and 5 will do, let's say 2. I plug it into the y prime. 2 minus 1, 2 minus 5, that's a negative value. You don't need to find the exact value what it is, right? In this case it's like what? Minus 3, right? But it doesn't matter. All you care about is the sign of the derivative. So if I start between 1 and 5, the solution decreases. Finally, if I pick a test point below 1, let's say 0, plug it into the ODE, and that gives me a positive value. So if I start below 1, that means the solution increases. So from this phase line, we can quickly see that the nearby solutions approach 1. Right? So if I start close to 1, eventually the solution converges to 1. So this will be the stable equilibrium point. And here the solution moves away from it. And so this will be unstable. So we're going to do another example pretty soon, but that's the main idea on how to analyze the stability for the single ODE. It's the easiest possible stability analysis. In the system case, things are a little bit more complicated, as you will see later. But in the single ODE case, when you have autonomous equations, it's just a matter of using the, doing the sign table. Before I actually move on to the next example, you will see that actually we're going to run this example or something similar to it in the plotter, so you will see it in the last part of today's lecture. But what you will see in the plotter, because the plotter gives you y with respect to t, you will see the equilibrium points, the equilibrium solution as horizontal lines, right? Because these are functions of y with respect to t. So this will be 1, this will be 5. And because 1 is stable, you will see that nearby solutions converge to it. So it will look like a horizontal asymptote, right? That's how a stable equilibrium point looks like as a function of t. And solutions starting close to 5 will diverge, will move away from 5, like that, either above or below toward 1, right? So again, unstable, stable. So the phase line is really telling you just the stability if you don't care about what happens with t. If you don't care about the actual value of y with respect to t, you only care about whether it approaches the equilibrium point or not, then the phase line simply tells you the motion along the y-axis. So let's conclude this part of the lecture with another example. Let's use one with 3 equilibrium points. Let's say y prime is equal to 3 minus y minus 1, and let's put actually a negative equilibrium point as well. Let's say y plus 2. When one sets this equal to 0, we have 3 equilibrium points, 3, 1, and minus 2. Yeah, if you set each parenthesis equal to 0. Once again, the phase line. And make sure you put the equilibrium points in order, 3, 1, minus 2 over here. And by the way, this sign table, you can do it in your mind. Just aim to do it faster. You don't have to write this table. I'm going to write it down just to make it clear what's the process when establishing these equilibrium points, stability. So you're going to have test values of y, and here you're going to have, of course, f of y. So aim to do this mentally. It's important to be also efficient so that you don't take too much time when you do this stuff. So a test point above 3, let's say 4. So 3 minus 4, 4 minus 1, 4 plus 2. It's kind of out of range here. So let me actually do it again. A little bit closer here so that it's not out of range. Right, so y, 3 minus y minus 1, y plus 2. We plug in 4. So we have 3 minus 4, 4 minus 1, 4 plus 2. Negative, positive, positive. So that's going to be negative. Still out of range. Over there. So negative, that means the solution approaches 3 if you start above it. Let's pick a test point between 1 and 3. So let's say I pick 2. So that means 3 minus 2, 2 minus 1, 2 plus 2. Positive, positive, positive. Solution moves up. Between 1 and minus 2, I think the easiest thing to pick as a test point is 0. So we have 3 minus 0, 0 minus 1, 0 plus 2, positive, negative, positive, multiply, that's negative. I'm always at the end of the margin there. So anyway, below, so what did I say? Negative, right? So that means the solution moves back, moves down. Below minus 2, let's say a peak at test point minus 3. We have 3. Here we have to be careful, of course, with the signs, right? So if you plug in minus 3, that's 3 minus negative 3. So that's going to be 3 plus 3 eventually, right? Negative 3 minus 1, and then negative 3 plus 2. What do I get here? Positive, negative, negative. So that's going to be overall positive, right? This expression. You may wonder whether the sign alternates all the time. It doesn't all the time. I mean, if the exponents here are even, the sign won't change. But that'll be still an unstable point because it means that it doesn't approach the point from both directions. So this will be stable. This will be unstable. And finally, this will be stable. So I'm going to run a couple of these examples with Camtasia. So once again, the Camtasia is essentially a software that records what I do on the computer. It's something you must do as well. So you'll see it as an example, but immediately run those examples yourselves so that you can check these results. So that's it for today with today's lecture. I'll see you next time.